In this video, we will talk about Newton-Euler's method for deriving the dynamic equations of the wheeled mobile robots. Newton's method is another main formulation to derive the governing equations of the dynamics of a mechanical system. This formulation relates forces and torques to the linear and rotational accelerations of the body masses. In this approach, using free body diagram, we isolate the wheeled mobile robot into its parts, namely the chassis and its wheels, and account for all the forces and torques acting on the parts. So the first and most important step in Newton-Euler dynamic modeling is to draw the free body diagram of the system and to analyze the forces acting on it. After drawing the free body diagram and determining the forces and torques on each part, Newton's and Euler's equation are written. For example, for this rigid object that moves in the plane, Newton's equation in the x direction is Fx equals m times v dot x, in which m is the mass, and v dot x is the absolute acceleration in the x direction. In the direction of y, the equations are similar, and the Euler equation is written for this rigid body, as you can see here, in which tau z is the result of all torques around the z-axis passing through the center of mass. Here is the center of mass of this body, and J is the moment of inertia around the z axis, and here omega dot z is the angular acceleration. Next, we explain the Newton and Euler method for deriving the dynamic equations of the wheeled robot with an example. We consider again diff drive mobile robot. You can see its chassis and the wheels on this slide, and the front wheel here is inactive, and the left and the right wheels in the back are active wheels. We consider the center of mass of the robot at point C, and XC and YC represent the location of the center of mass with respect to the body frame. The distance of center of mass from point A is equal to L, and the radius of the wheels is equal to R, and the distance between two wheels is equal to 2D. Now we will draw the free body diagram of chassis. We separate the left wheel. This wheel applies two forces to the chassis in the plane, FUL, which is longitudinal force, and FWL, which is lateral force. FUL is the result of the wheels drive motor, and the FWL force is the result of the no side slipping constraint. Similarly, the same can be said about the right wheel. It should be noted that another force enters from the wheel, which is the gravitational force, that is a reaction force, but this force is not in the XY plane, and we assume that the wheels of the robot always remain in contact with the ground. So we do not consider gravitational force. According to Newton's third law, the opposite forces are applied to the wheels and should be included in the free body diagram of wheels. We also assume that VU and AU and also VW and AW represents the velocity and acceleration of the center of mass C in the local frame attached to the chassis. And it should be also noted that the front wheel is inactive and it doesn't exert any force to the chassis. A free body diagram can also be drawn for the wheel. For example, here you can see the free body diagram of the right wheel. You can see the ground reaction force, NR, friction force in the longitudinal direction, and it acts on the wheel plane, vertical force from the chassis, N prime R, wheel weight force, MW times G, driving or brake torques, denoted by tau R. Also, the component of the friction force in the W direction and the force from the chassis in the W direction are also included, which are not shown in this figure. W is the lateral direction, so we have a force in the lateral direction that is not shown in this figure, and we have also a friction force in the W direction, and that is inward and is not shown in this figure. Here we are not interested in the wheel dynamics, and our focus is on the chassis. The only thing we will take from here is that, ignoring the moment of inertia of the wheel, we will have FUR equals tau R over R, in which R is the radius of the wheel, and FUR is the force that acts in the longitudinal direction. And similarly, for the left wheel, we will have FUL equals tau L over R. The vector of velocity of the robot in the local frame is equal to VU plus VW. Considering that these vectors change their size and direction with time, using the vector derivative of rigid in the rigid body dynamics, the acceleration of the center of mass, which is the derivation of the velocity, will be equal to this equation. Yeah, and here you can see this term that implies the derivation of the vector, these vectors. With algebraic manipulation, finally the components of the acceleration of the center of mass in the local coordinate system will be in the form of equation 19 and 12. So AU and AW are obtained as you can see here. The next step is to write the Newton's second law for motion as well as the Euler equation in the robot frame and find the relationship between the forces, torques, and accelerations. The diff-drive robot exhibits two types of motion: translation in the U and W directions, and a rotation around the vertical axis at the center of mass. So the dynamic equations are, as you can see here, M times AU equals FUL plus FUR, FUR, and MAW equals FWL minus FWR. And for the moment equation, we will have J times theta double dot equals FUR minus FUL times D, D is the distance between two forces. Distance between the force and the center point, plus FWR minus FWL times L. L is the distance between A and C. Substituting the acceleration terms from 19 and 20, we get these equations, equations 24, 25, and 26. The absence of slipping or pure rolling in the longitudinal direction and no sliding in the lateral direction creates independence between the longitudinal, lateral, and angular velocities and simplifies the dynamic equations. These non-holonomic constraints are taken into account by defining the velocity of the center point A in the local frame and forcing it to be zero in the lateral direction. The lateral velocity of point A in the local frame is VW minus L theta dot. Therefore, in the absence of lateral slippage, we will have VW equals L theta dot. You can see here again equation 27. Next, if we substitute equation 27 in equations 24 and 25 and combining it with equation 26, we will have these equations 27 and 28. Here we have just two equations and one equation vanishes. So these are the equations of motions of the robot. Dynamic equations can now easily be transformed to show the actuator torques applied to the wheels, similar to the notations used in the Lagrange approach. We have seen before that FUL equals tau L over R and FUL equals tau L over R. So equations 29 and 30 are obtained by substituting these relations to the equations 27 and 28. Next, these two equations can be written in the matrix form, as you can see here. Let's compare the equation 31, which has been obtained by Newton-Euler approach, with what we have obtained by Lagrange method. The equations in the red boxes are obtained by Lagrange approach, and we have shown that before. There we have considered the center of mass at the reference point, that is point A. But here in the Newton-Euler approach, we have considered the center of mass here at the point C. Therefore, in order to make a correct comparison, we should put zero value instead of L in equation 31. If we do that, we will obtain this equation from equation 31. As you can see, equation 31 finally will be similar to what we have obtained using the Lagrange approach. If you compare this equation in the blue box with the equation we have obtained from the Lagrange approach, you will see that both the equations are equivalent. Theta double dot is equivalent to omega dot, and both v dot and v dot u represent longitudinal accelerations. As a general result, we can say that both formulations are equivalent, and we can validate one solution with another by checking consistency. If we solve the equations for the inputs or the torques, we get the green box equations. Given the longitudinal acceleration and angular acceleration, we can compute the driving or braking torques. As we have seen, the equations can be written both for acceleration and torques. Here is the equations for accelerations, and here is the dynamic equation for the torques. Generally, in the dynamics of mobile robots, similar to other dynamical systems, there are two problems. Forward dynamics, in which for a given input vector, we calculate the resulting motion. Forward dynamic formulation is useful for simulation and analysis purposes. In inverse dynamics, for a given desired trajectory, the required input vector is found. This formulation is useful for control of the robot. In the case of the diff drive robot, if equations of motions are written in this form, it will be suitable for the forward dynamics problem and can be used in the simulation. If the equations are written in this form, it will be suitable for solving the inverse dynamic problem and calculating the inputs. This formulation and these equations are useful in control. Now, as another example, let's consider the dynamics of a robot with 3 omni wheels. The body frame is here in the middle of the triangle. It is considered to be the center of mass. So the center of mass is here at the C. As you know, in omni wheels, the wheel is free to move in the side direction. And as a result, there is no constraint for sideway motion. Similar to diff drive robot, if the acceleration of the center of mass is given, the free diagram for the chassis can be drawn as you can see here. We have 3 forces, F1, F2, F3 for the wheels, and the angle of these forces with the U direction are phi 1, phi 2, and phi 3 respectively. Finally, you can see the equations, the resultant forces in the local frame as seen here. The torque of these forces around the vertical axis passing through the center of mass also will be like this equation. mcz equals F1 plus F2 plus F3 times L. L is the distance between the center of the wheel and the center of mass of the chassis. And finally, the equations of motion are displaced as shown in this box. The number of equations is 3. As seen, the lack of lateral sliding constraint does not reduce the number of equations. So there is no constraint here, and the number of equations in the plane will be 3. Try to write these equations in a matrix form, and also try to get the inverse dynamic form of these equations. As we discussed earlier, there are two problems related to the dynamics. Forward dynamics, in which for a given input vector we calculate the resulting motion. In inverse dynamics, for a given desired trajectory, the required input vector is found. Now, the question is, what if for a system the both inputs and motions are unknown? Are such problems solvable? Think about this. Here is a hint that can help you think about predictive dynamics. In predictive dynamics, we formulate the problem like F minus m times a equals 0. And think about the relation between predictive dynamic and model predictive control. These equations are equations of motion for a rigid body moving in the three-dimensional space. If you remember, in slide number 29, we reduced these equations and we just used 3 of equations in the plane. For a planar motion, we just wrote these equations. So think about under what assumption we reduce these equations to the equations that we wrote in the slide number 29. Well, so far we have talked about the kinematics and dynamics of wheeled mobile robots. In the next chapter, we will start paths and trajectory planning for this kind of robots.